Okay, good morning, everyone. Today I will first introduce the differential form of the momentum equations. So there are many equations today. So I need around 1 hour to finish to introduce the differential form of a momentum equation. So this slide just remind you in previous chapters, I already finished the to introduce the differential form of the continuity equations. As you see here, the equations show in the patterns there is a density change with the time plus the divergence of the density multiply the velocity field factors. So this is very important, always equal to 0. This is our continuity equations. And as we say that if the flow is in compressible flow, and then we can rewrite the equations to be the only velocity field factor divergence is equal to 0. Okay, this is very useful if we consider that the flow condition is incompressible, and then we know that the divergence of the flow velocity factor is equal to 0, and the left hand side, this is the general continuity equations. Even though the flow condition is not incompressible flow, but the velocity flow field still satisfy these equations. And we also know that if we right now we are discussing the flow is non-rotational flow. So we know that the flow is non-rotational flow, and then we know that the curl of the flow velocity field is also equal to 0. So this is two important equations. One is related to divergence, another is related to the curl of the flow velocities. So equal to 0 is for the incompressible flow and the non-rotational flow, and we know that the curl of the flow velocity is equal to 0. So now we move to the slide related to the differential form of the momentum equations. So if we would like to understand the differential form of the momentum equations, so we need to pick up one fluid particle, and this fluid particle is very small. So we have the delta x, delta y, and the delta z, and then we initially consider that the momentum equations. We know that the left-hand side is sum of the external force, and the right-hand side is the momentum change with the time in the control volumes, and plus the momentum flow patterns around the curved surface. And as we know, our target right now is the velocity field. So we have the velocity along the x directions is u, and the velocity along the y direction is v, and the velocity along the z direction is w. So our target is the velocity field factors. And directly tell you the differential form of the momentum equation can be used to determine the velocity field vectors. So usually we call that is also the Navier-Stokes equations. And apply the Navier-Stokes equation, then we can know the velocity field u, v, w. Okay, so now we first target is the external force, and we fix our target directions is the x directions. So how many force we have along the x directions? So we can divide it into the body force and the pressure force. The pressure force is the normal force for the fluid problems. And for these problems, we have the third force. We call that is a shear force. As we know, previous chapters, we always ignore the conditions for the viscous effect, but here the viscous effect need to take into account. So we have the shear force which is related to the viscous effect. We call that is Fs. So we assume our external force can be divided into the three parts. The first is the body force, and the second is the pressure force, and the third part is the shear force. Okay, so what is the body force? If you see here, this is the final answers for the external force, and we assume we have the acceleration Fx related to the body force, and multiply the rho with fluid densities, and you see we have the pressure difference gradients, and there is some force related to the viscous force tau. Okay, so so for the body force is quite simple because we just the density multiply the acceleration related to the x directions. So we are moved to the next is the pressure force. So how can we estimate the pressure force for a small fluid particle? So again, we just push here. Here is the center of our cubic fluid particle, and we assume the pressures at the center point is P0, and in this point we call that is the pressure right, and here is the pressure left. Okay, so in that conditions we have we can estimate the pressure right. The pressure right we can equal to the pressure 0 plus the dP dx. This is the pressure gradient along the x directions, and the plot multiplied the delta x divided 2. Okay, because the total length along the x directions is delta x. Okay, and then we have the pressure left is equal to the T0 minus the dP dx multiply the delta x divided 2. So what is the pressure force F Fp is equal to the force left pressure force left is positive because the arrow direction is the positive x directions, and the pressure force right is the minus because you see the arrow here is going to left. So actually here we have the pressure force left minus the pressure force right. Okay, so as we know how to convert the pressure to the pressure force, we need to multiply the areas. So this is area A is equal to the dy is delta y multiplied delta z. Okay, this is our coordinate. Okay, x, y, and z. So the area is delta y multiplied delta z. So we know that there is a b0 minus dp dx delta x divided 2. This is the pressures left minus the pressure right. Okay, dp dx multiply the delta x divided 2 and multiply the pressure delta y and delta z. Okay, so you see based on this equation, the P0 can cancel out. So finally, the pressure force is equal to the minus delta dp dx multiply delta x, delta y, and delta z. So the pressure force is equal to the minus pressure gradients along the x and multiply delta x, delta y, and delta z. Here is the total volumes of our fluid particles. Okay, so that's why here the second items for the external force, we call that is the pressure force related to the pressure gradients along the x directions. So now, how can we have the force from the shear force? So this is our first time to discuss the shear force related to the viscous effect. As you see, there are three items related to the shear force. We call that is the tau xx here and the tau yx and the tau zx. So there are two index related to xx, yx, and zx. So what is meanings of the index? As I can so I change the coordinate. There is a y, there is x, and there is a z. Okay, because I changed the coordinate, and it's better to introduce the tau xx, tau yx, and tau zx. As you see the top of the cubit here, we have the surface, and this is surface is our top of the cubit, and we know that the normal factors of this surface is along the y directions, right? And one shear force acting on this surface along the x directions, and we call that the shear stress on this surface along the x directions. We call that is tau yx. So that means the first index y indicates the surface with the normal factor along the y directions, and the second index is indicate the force directions. In that case, the force is along the x directions. And so that's why in the right surface here, we call that is the tau xx, because the normal factor of this surface is x directions, and the force also acting on this surface with the x directions. Okay, so now again, we try to describe the force contributed from the shear force. Okay, so we can assume the center of the qubit is the tau zeros, and then we can try to understand the, the shear stress on the surface. So if we consider the x directions for the shear force, so again, the tau zero right is equal to, sorry, we consider x direction, so the tau x and the surface is on the right and left along the x directions. So the tau x right is equal to the tau x zero plus the tau d tau x dx and multiply the delta x divided 2. This is our tau x right is equal to here. And what is our tau x left is equal to the tau x zero plus the tau x dx and the delta x divided 2. But here, our delta x is moved to the left, so there is a minus. Okay, and the difference compared to the pressure, the tau x right is the positive. You see the arrow direction is the positive x directions. So in contrast to the left, it should be the minus. So for the tau x it should be equal to the tau x right minus the tau x left. So we know that the answer, the tau zero x can cancel out. So for this, we only have the tau x dx multiplied delta x. Then the surface area for this problems is the for this phase is the delta y multiplied delta z. Okay, so the force related to tau x is the tau x multiplied area. So we have the tau x dy, delta x, delta y, and delta z. Okay, and then we still have another surface. So now we discuss the surface or normal factor along the y directions. So we are discuss with the tau y x, and this is also the tau y x right is the tau y x 0 plus the d tau y x. This is the change, the gradient change of the tau y x along the y direction. So there is the d y, and there is a delta y divided 2, and we have a tau y x left, and the tau y x 0 minus the tau y x dy delta y divided 2. So again, we have the tau y x is equal to the tau y x right minus the tau y x left. So it's equal to the d tau y x dy multiplied delta y. So in that case, our area of the surface is the delta x multiplied delta z. Okay, this is our area. So we know that f tau y x is related to the d tau y x dy multiply the delta x, delta y, and delta z. Okay, so similar to the f tau xx and f tau y x, the f tau z x should be equal to the d tau z x d z multiply delta s, delta y, and delta z. So we have the f tau x, f tau y x, and f tau z x. All of the shear force with the acting direction along the x directions and but acting on the different surface. Okay, the top, the right, and the bottoms, and also the in these directions. Okay, so this is our external force related to the body force, pressure force, and the shear force, and multiply the total volumes of the small fluid qubit. Okay, so right now we try to deal the problem on the right hand side. So as you see here, the right hand side, we have different integrations along the different domains. So in the control volume, we integrate along the total volumes. But for the control surface, we integrate with the cross-section areas. So for this, we know that the first item is d and dt, and there is the rho u d total volumes, so it's integrate around the volumes. And the right hand side here, we would like to exchange the integrate along the areas to the volumes. So we consider the divergence theory tells the physical property flux integrates along the cross-section area is equal to the divergence of the physical properties integrated along the volumes. So if we would like to replace the integrate operator along the surface to be the volumes, so we need to rewrite here is the divergence, the rho u b factors, and we can replace the area to the volumes. It's just based on the divergence theories. Then if we go back to see our conditions, right now we only consider the small qubit particles, so we don't need to deal the problem with the integrate, because we only have the small volumes delta x, delta y, and delta z is our delta V volumes. So we remove the integrate operators here, and we only have the D, and our problem is the low U, and multiply the small volume is delta X, delta Y, and delta Z. And the right hand side, the second item here is plus the divergence of the low UV vectors and multiply the delta X, delta Y, and delta Z. So we only focus on the problem with the DT low U plus the divergence of the low UV vectors, and then we take the small volumes outside. Okay, this is right now our problems. We need to the differentials and the divergent operators for this equation. So by layer we use the U velocities, and the layer is V vectors. The U velocity is the fluid flow velocity in the control volumes, and the V vectors is because we would like to compute the mass flow rate, so we need to use the V factors here. So how to solve these problems? So we need more space. So we know that we have the low U and the T plus the divergence low UV vectors. Okay, so we have the partial differential. So if we fix a U, and there is the low dt, and if we fix a rho, so there is a du dt, and there is a divergent operator, so we just expand. There is a dx I directions plus dy z directions, and plus dz k directions, and the left hand side is right hand side here is plot with the dou u I directions plus dou u v z direction plus dou u w k directions. So for the divergence operators, we know that we keep here is a u d rho d t plus rho d u d t, and then for the divergence computings, we only have the items for the I, J, J, and K, K. So there is the plus I for the IR is the dx, and the inside the low u, and the J items is plus dy, and the inside is low uv, and the plus the kk items is the dz, and the inside is low uw, and we expand also partial differential for the final third items. Okay, so this is u below dt plus the low du dt plus the low u here. We consider these items. The inside is the du dx, and we can also put the u outside, and the inside is a low u dx. Okay, and for the sake these items, we know that we have the low v and the du dy and the plus the u take outside and the inside the low v dy. And for the z, the final item here is can be the low w du dz plus the u take outside and the low w dz. So if we put all of the parameter with the u parameters together, so we have pick up all the parameter with the u here and put their together. We have the u and the inside is the low dt, right? And there take a u outside and this is the low u dx and the plus here the low v dy and here is the low w dz and this other parameters it still have the low du dt and here low u du dx and plus the low v du dy and the plus here low w du dz. Okay, so if we compare the final answers shown here, we only have the term in here, but the first one here should be equal to 0. That's why. So if we take a look, this is quite similar to our differential form of the continuity equations. As we know that previous slide showed the differential form of the continuity equation is the low dt plus gradient divergence, the low v factors equal to 0. So in that condition, we don't need to consider the flow condition is incompressible flow or steady flow because this is a general form for the continuity equations. So for this item, we'll always satisfy continuity equation, so it's always equal to 0. So finally, for our d low u dt plus the divergence of the low uv factors is equal to the low du dt plus the low u du dx plus the low v du dy plus the low w du dz. Okay, so this is our final for the right hand side. This is the control value integration and the integrate along the control surface items. Okay, so this is the left hand side is related to our external force. So in here, we need to try to deal the problem with the tau xx, tau yx, and the tau zx. So as you remember in the chapter 2, when I introduced the shear stress We know the shear stress is related to the viscosity parameters and also related to the velocity gradients, like here show, you know, the du, dy plus the dv, dx. So this is, we call that is the flow velocity gradients. So the relationship between the shear stress and the shear force, shear stress and the velocity gradient is the viscosity parameters. Okay, so simply in here, I just tell you, we assume the fluid is Newton fluid. Then I tell you that tau xx is equal to the 2 times mu multiplied du dx. And the tau yx is the mu multiplied du dx plus the dv du dy plus the dv dx. And the tau zx is equal to the mu multiplied du dz and the dw dx. So this our first assumptions, our fluid particle is Newton fluid. Then we satisfy the following equations. Okay, so we can follow these ideas, and so we know that the tau xx for the first item here, dx is equal to the 2 times mu the u squared and the dx squared. And what is the second item here is a dy, but there is a tau yx, right? So we know that it's a d dy and multiply the mu here, and there is a du dy plus the dv dx. Okay, so we just put the dy inside. So there is a mu d u squared and the dy squared. And there is plus the d dy, and there is dv dx. And we assume, we just based on the Clairaut series, we know we can exchange the dy dy multiplied dv dx is equal to the d dx and the dv dy. It's just based on Clairaut series, so we can exchange the ref domains. So we can rewrite the equation final is equal to the mu d u squared dy squared plus the mu d x dv dy. Okay, so and then we can also know that the third part, the tau zx dv, you can write to be the mu d u squared and d squared plus the mu because this is d and there is u dz and the dw dx, so we can rewrite to here is the dx, but the final item here is the dw. dz. Okay, so you just take a look here and here and here. So we can summary the d tau x dx plus the d tau yx dy and the plus d tau zx dz is equal to the 2 times mu d u squared dx squared plus the mu d squared mu dy squared plus the mu d d squared and the dx sorry d dx dv dy and the plus the here the mu du squared dv squared plus the mu d dx dw dz. Okay, so if you use reorganize the equation, you know that we just here what we have the square mu dx square and there is plus the du squared dy squared and there is du squared dz squared and there are additional items mu. Again we have the d u squared dx squared, but there is we have plus the d dx dv dy and there is the d dx dw dz. So for these items, we can also take the dx divided dx outside. So inside we only have the du dx dv dy and the dw dz, right? Here. So we assume our fluid is incompressible fluid, and then we know that the fluid need to satisfy the divergence of the flow velocity factor is always to equal 0. So this is item totally will equal to 0. So for the shear stress part here, we can rewrite the equation to be a second derivative operators. This is we call that the Laplace operators here. So if we summarize all directions, so this is we only consider the directions along the x, and this is a y, and this is a z. So we can combine all of the directions and combine the equations into the vectors balance. So actually we have the tau g, okay, that is related to the fx, fy, and fz. This is the acceleration related to the body force. So our famous body force is the weight. In the second, we have the pressure force gradients. But notice that there is the minus operators, and we also the plus, the mu, the plus operators for the flow fluid particles. So this is the item related to the shear force because we need to consider the viscous effect. And the right hand side is equal to the density multiplied the acceleration operators. So actually, this is derivative operators equal to the low dt and dt plus the low u d dx plus the low v d dy and plus the low w d dz. Okay, this is the derivative operators for our problems. So if you take a look for this part is always dt. So we call that is a local accelerations. And this is the part always is the u dx and the v dy, the w dz, and also there's a u dx v dy and the w dd. So we call that is a convective accelerations. So this is similar to our previous slide. We tell you the Euler equations. We can divide the acceleration to local acceleration and convective accelerations. Okay, so this is our final Navier-Stokes equations. We have the body force, pressure force, shear force, and the total related to the density multiplied the acceleration. Okay, so this is also followed the Newton's second law. Force is equal to ma. Okay, so let's go back uh, to the exercise. As I mentioned, since we know that the Navier-Stokes, so we can determine the flow velocity field for any conditions. Okay, so we just first exercise, we know that the put flow is always be applied to the duplication problems. Okay, so we always know that the upper plate move with the u velocity, and the thickness of the duplication liquid is L. And based on the plot, we know that the velocity field with the linear gradients and the velocity always along the x directions. There is a string directions, but it is similar to the x, arrow to the x. So we know that we only have the velocity along the x direction, and the velocity should be the functions of the y. And we know that actually the answers for this velocity u is the u divided the thickness of the duplication liquid and multiplied y. So based on this formula, we know that the bottom here velocity is 0, and the upper here the velocity is u. Okay, so how can we determine the velocity field based on Navier-Stokes equations? So we only consider the direction along the x because this is like the 1D dimension problems. So we know that the low g we only have the x directions, and the minus the pressure gradients. So there is a dp dx along the x directions. And the plus here is the mu. The inside is the du squared dx squared plus the du squared dy squared, and then plus the du squared dv squared. And the right hand side, we know that is a low du dt. We only have a u velocity along the x directions, and then plus the low u du dx and plus low v du dy plus low w du z. This is an ideal stalk along the x directions. And since the first item is the body force, but along the x direction we don't have gravity, so this is equal to 0. And for our problem, we just expose on the atmosphere environment, so the gauge pressure change is equal to 0, so we don't have the pressure gradient. And then, as we know, our fluid particle only with the velocity flow along the u directions and the u as a function of the y. So we don't have the first item and the third item here. And we assume this problem is steady state flow. So the u velocity didn't change with the time. So this is also equal to 0. And here is not the function of the x, and also not the function of the z. The u is a function of the y, so we have these values. Here we don't have the v velocity. Okay, so this is also equal to 0. So finally, we know that based on the Navier-Stokes equation, we only have du squared dy squared equal to 0. And based on these conditions, what are the boundary conditions we have? We know that the boundary conditions, first we have the u y equal to 0 and the velocity is 0. And the u y equal to L thickness and the velocity is the u. So we know that we do the integration for these items. We know that u y should be equal to the C1 constant values, C1 constant values, and we have the y in the plus the C2, right? Because we take the first differentials, then we only have the C1, and we do the second differentials is equal to 0. So we just put the boundary condition inside to these equations. So first, we know that the y equal to 0 in the here, and so the C2 is 0. If the y is L, so we know that the y equal to L is equal to u, and then it's a C1 u, right? And the C2 we already know is equal to 0. So finally, we know that the C1 is equal to U divided, here the is L divided L. Okay, so finally, we know that the U as function of the Y is equal to the U divided L multiplied Y. Proof. So this is the same, similar to, it's the same as with the answer. We already know that the function shown here. So that means we don't need to know the velocity first, because based on the Navier-Stokes, we can easily to determine the flow velocity field. Okay, so we move to the second exercise is a visual flow, like the nature channel flow conditions. So again, we know that actually based on the figure tell us the velocity profile is follow the parabolic velocity profile. But how to determine the velocity profile for this channel flow? So we based on the Navier-Stokes equation shown here, and we also consider our coordinate is this is a y direction and this is a string direction, it's parallel to the x direction. And we have the channel width is E. So how can we prove the velocity profile? And as you see, this is some assumptions is that each plate is wide enough so that the end effects caused by the side walls of the channel can be neglected. And our flow condition is nominal flow for real numbers below the 1000. Okay, so this is only the condition for the nominal flow, not for the turbulent flow. So again, we just follow the Navier-Stokes. So we have a G x only consider the x directions and plus minus the pressure difference. So here we consider the piezometric pressures. So this is the P plus the gamma Z, and again this item is related to the du dx squared plus the du dy squared and the du dv squared, and the right hand side we still have a low du dt plus low u dx, low v du dy, low w du dz. So again, we don't have the gravities, and right now this is for the channel flow. So we will have the inside pressure difference. So we have the pressure gradients, and the u only a function along the y directions. Only the function of the y and the u is along the x directions. So u is not a function of x and also not a function of z. So we cancel out the gradient related to the x and the z. And this is also satisfy the steady state flow. So we don't have these items. And then we don't have any velocity along the y directions. So we don't have these items. So finally, what do we have? We have the minus dx, the piezometric pressures gamma v, and the plus the u dy squared equal to 0. Okay, so we can make the balance, and we know that the du dy squared is equal to the mu over 1 d and dx and the piezometric pressures. Okay, so for this problem, we have the two boundary conditions. We know that the u y equal to 0, the velocity is 0, and then also u equal to thickness, also the velocity equal to 0. So this is our two boundary conditions. And then we know that we do the integration, u will be equal to the mu over 1 and the d dx, the pressure, piezometric pressures, and there is a 2 over y squared and the plus the C1y and the plus the C2. And we have the two boundary conditions, so we can solve the C1 and the C2 coefficients. Okay, so you can do by yourself. And the final, we know that the velocity can be represented here. As you see, there is a by minus y squared. This is functions for the parabolic velocities. Okay, so we prove why the velocity is the parabolic velocity profile. Okay, so due to the time limit, so I don't show the example for the C1, C2 coefficient here. So you can build a problem by yourself because we already have the two boundary conditions. So you can solve the two unknown parameters C1, C2. Okay, so if you are interested in aforementioned topic is related to the course of the computational fluid dynamics. We call that is the 计算流体动力学. Okay, so this is a very interesting if we can use the computer numerical methods to solve and deal the Navier-Stokes, so we can compute the velocity field very quickly. OK， 好，那我们来说明一下今天我们的考试题目。OK， 所以今天考试题目只有一题。希望大家这次有充裕的时间可以去计算这个有一题的考题。上个礼拜我们有礼拜五上个礼拜我们有说到我们一定会考火箭的问题，那我们就只考一题的火箭。那其实这些英文的描述在上课的时候几乎是一模一样的。一个是我们有一个火箭，我们知道它的上升速度是用 VII，我们有一个 VII 的这个上升的火箭的上升速度，然后这个上升速度 VII 是相对于地面，然后我们有一个喷气，喷气作用在这里，喷出去的气体的速度是 V1 相对于火箭，然后面积是 A1，喷出去的气体相对于这个截面积是 A1，所以我们可以知道，我们可以产生了一个在这样子的状况下，我们可以产生一个 gauge pressure P1，所以我们知道 P1 可以乘上 A1，可以贡献的是 pressure force。在这个出口的位置有一个 pressure force， 然后我们跟你说这个 thrust 的 force T 与这个动量喷气的这个动量变化率加上这个 pressure force， 那就是我们这个推进力 thrust。那我们在做这个分析的时候，我们忽略 body force W 跟 drag force， 所以我们最后可以描述当有多少质量的这个燃烧，我们最后可以得到了多少的这个终端速度，就火箭的这个终端速度。所以燃烧的这个剩余的这个质量越小的话，这个火箭速度会越快。那所以第一个，我们请你用动量方程跟连续方程去验证公式一。这个我们在上个礼拜我教得很清楚。那我们假设一开始火箭速度是0，当时间等于0的时候，然后我们有说到说，其实瞬间火箭所带有的质量应该是它原本的质量减掉它的这个质量流率乘上发生的经过多少时间 t， 所以 m0 是它起始的质量，然后经过多少时间 t， 那 mf 是它剩余的这个最后的质量，剩余的这个质量，然后 EO 是燃烧多少质量所带有的火箭速度，那一般我们说这个是终端速度 ，OK， 所以 dA 小 t 的我这边有50%，其实就是要你去推导怎么得到这个公式，然后第二件事情是，那我请问你，如果我现在提供你这个 thrust 跟这个 mass flow rate，其实就是这个 T 跟 mass flow rate 的 ratio， 那我提供你最后剩余的火箭的质量是50，那请你计算起始的这个火箭质量到底是多少，然后我最后这个速度 VBO 是7200每秒公尺。那请问一开始需要多少的这个火箭大概多少的质量冲上去，才可以满足这个条件？哦，好，那同学如果没有问题的话，就可以开始作答。那记得我们在算这个 V1 的时候，我们在计算这个 V1 跟这里的这个 mass flow rate 的时候，要注意一下速度的这个相对的这个坐标。好，那我们就一样考到9:50，那大家记得在9:55以前要缴交你的这个作答过程。 好，各位同学，大概还剩下3分钟。好，时间差不多了，同学们记得要在9点55分之前把作业这个作答过程上传。好，那我们今天课就上到这里。